Hello, welcome back. The title of this lesson is Radicals Can Be Written as Fractional Exponents. Now this is, I'm going to warn you right away, just a motivation lesson. It's going to teach you something very, very, very important. But also it's going to teach you something that's usually not taught until a little bit later in the sequence. Because what's going to end up happening is in the next lesson, I'm going to introduce a bunch of properties of radicals. Like what happens when you multiply radicals? What happens when you divide radicals? What happens when you have radicals raised to an exponent? What happens when you have exponents raised to a radical? All those things. And I'm going to give you a bunch of properties, and it's going to look really confusing because you're going to look at them and say, how is that true? How do you know that when you multiply these radicals, this is what happens? Because most books are not going to prove it to you. They're just going to tell you, give you a table, and say, here's what happens when you multiply radicals. Here's what happens when you divide radicals. Here's what happens when you take a radical and raise it to a fourth power, or whatever. But what I'm going to do now is clue you in on something that you are generally taught a little bit later in algebra. It's very simple to understand, but it makes all of those properties of radicals very simple to comprehend. And that is the following. I'm going to give you the punchline right now, and then the rest of the time I'm going to spend proving it to you and showing you how it's true. So when you come out of this, you should be convinced of the following thing. Here it is. All of these radicals, the square roots, the cube roots, the fourth roots, the fifth roots, the sixth, any root you can think of, can always be written as an exponent, Like x to the second is an exponent. But the difference is, anytime you have a radical, it's not an exponent with a whole number. It's an exponent with a fraction. So you're going to learn later on in your algebra, we're going to get a whole new, sequence of lessons way down the line where I'm going to introduce fractional exponents. Some books will call it fractional exponents. Some books will call them rational exponents because remember, rational means you can represent it as a fraction, right? The bottom line is rational exponents or fractional exponents really are all of these. They're exactly equivalent to all of these cube roots and all this stuff. So let me get the punchline. Actually, the way I drew it on my paper is a little different than the way I want to introduce it to you here. I'm going to give you the punchline first so you can see how crazy it looks, and then I'm going to show you why it's true and how easy it is to understand it. So that as we get into the properties of radicals in the next section, you're going to say, that's why they're that way, because they're all exponents. All right, so here's what it is. Here's the punchline. Here's something that you're not going to learn generally for a couple chapters later, but I want you to know it now. The square root of x is this thing we've been talking about, right? It's exactly the same thing as x raised to the fractional power 1/2. Now this blows your mind the first time you think about it. You're thinking, how can you have an exponent that's a fraction? Remember, we talked about exponents. X squared, it means x times x. X to the third means x times x times x. X to the fourth means x times x times x times x. X to the 1/2 means, what does it mean? It's weird. It doesn't make any sense. But by the end of this lesson, you will understand why it makes sense. But right now, don't worry about why. Follow me on into the how. Square root of x, because it's a 2 here, is x raised to the 1/2 power. Similarly, the cube root of x is x raised to the 1/3 power. Similarly, the fourth power of x, or the fourth root of x, I should say, is x to the 1/4. And by now you can see the pattern. Anything you put in here, the fifth root of x or whatever, is just x to the 1/5 power. So when you get a little bit farther in math and you get into physics and engineering and other things, or even calculus, most of the time you will most of the time not see radicals. I mean, sometimes you will, don't get me wrong, especially a square root, you'll see that. But oftentimes you will not see cube roots, fourth roots, and fifth roots. What you will see are equations with all of these exponents written as fractions. Why do you think that is? For now, you have to take it on faith with me that these things are equivalent. But the reason is, if I have a bunch of things multiplied together, like fourth root times a fifth root of this times a third root of this, it kind of gets a little cumbersome to draw those radicals and also put the little number, third root, fourth root. And also I have to teach you the properties of radicals. How do you even multiply them together? It seems hard. But if you know that these are equivalent, then if let's say I'm multiplying all three of these together in some big expression down the road, then I can instead write it like this, which actually, believe it or not, looks easier because I already know how to deal with exponents. I know what to do. If I multiply x to the 1/3 times x to the 1/4, I have to add the exponents. I mean, I know it's a pain. They're fractional exponents. You have to add fractions. But you still know what to do. You know to add them, right? If you raise a power raised to another power, like x to the whatever, fourth power, and again raise that to the fifth power, you multiply the exponents, right? We learned all of the rules of exponents. So what I'm trying to teach you is that because all of these radicals really are exponents, then all of the properties of exponents that we spent so much time learning also apply to radicals. So in the next lesson, I'm going to introduce what happens when I multiply radicals together. What happens when we add radicals? What happens when we divide radicals? What happens when we take radicals and raise them to a power, like fourth power or something? What happens when we do all these things? And what you're going to see now that I'm pointing it out to you is all of those rules are going to look very similar. You're going to roll them around your head and they're going to look really familiar, and that's because they're all exponent rules. They don't usually tell you that radicals really are fractional exponents until much later in the class. So you get to these radical properties and they don't make any sense where they come from. But I'm telling you now up in the beginning that all of these radicals really are exponents. They're just exponents with a fraction. And I know that doesn't make sense right now, but that's what they are. So if you ever have a situation where you're multiplying radicals together, it's the same thing as multiplying those. And even though they're fractional exponents, they still obey the same rules of exponents. So you don't have to learn anything new. That's the punchline. Now I want to go back to the beginning of my notes where I want to motivate why this is true. This is 100% true. Now I want to motivate why it's true. All right, so underneath here, I want you to recall a few things. All right, I want you to recall very simple things. I want you to recall the following. I want you to recall that 2 squared, what does it mean to square something? It means that 2 times 2, you multiply it by itself. How many times? This many times. And that's equal to 4, right? And also, you also learned the following. You learned, what am I going to use for my next one? Yeah, I'll use this one. You also learned that the square root of 4 is kind of like the opposite of squaring something. It's a square root. What happens is you write it as 2 times 2 in a factor tree and you circle it and the answer you get is 2. So do you see how these are kind of like opposites of each other? I mean, we all know this. We've talked about it before because 2 squared gives you 4. So the square root of 4 is 2. That's why they're opposites of one another, right? Let's do one more. I know this is review, but it's important to draw the parallel. We're going to get to the fractional exponents in a second. 3 squared is what? 3 times 3, which is what? Equal to 9. And you also now know that the square root of 9 is 3. You write it as 3 times 3, you pull the pair out, and you get a 3. Okay, you all know that. So what I'm going to do here is I'm going to say 3 times 3. All right, like this. Now I want to draw something, kind of point something out to you in a second. Well, let me get it on the board first, and then I want to point it out to you. All right. So if what I'm telling you is true, which you have to take it on faith for now, but if what I'm telling you is true, that the square root of 4 is 2, but that means that the square root of 4, right, really is the exact same thing as 4 raised to the power of 1/2. And I know it looks crazy the first time you see a fractional exponent, but what I'm basically telling you is the square root is basically whatever is under the radical to the 1/2 power, okay? Then what's basically happening here, that this is equal to, of course, 2. We all know the answer to it. And that the square root of 9, which we already wrote down here, was basically 9 to the 1/2 power, right? Which is equal to 3. Now here is the part where I need to start talking. I've got a bunch of notes here that I have written down, but here's where I have to start talking. And eventually, when I do enough talking, I hope it'll click with you that you'll understand what I'm trying to tell you. So what I'm saying is this fractional exponent, you look at the denominator of it. In this case, it's a square root, so it's a 2 denominator. The 2 means that when I draw a factor tree, I look for pairs of numbers. Pairs. In other words, what I'm doing is I'm writing all of the factors of 4 that I can, but I'm only letting half of them count. Why? Because the fraction is 1/2. I'm only letting half of them count. So I only count 1/2 of what I've written down as far as the duplicates go, and I pull it out, and that's the answer. That's how fractional exponents make sense. I'm going to have to repeat it several times for you to understand it, but that's the essence of it. When you raise something to the 1/2 power, the first thing you think of is, what does that mean? I mean, 3 squared is 9, I get that. 3, to this and this, I get that. But 3 to the 1/2, what does it mean? It means that I draw a factor tree, and I write all the factors, but I don't multiply them like regular exponents. I collect them in terms of groupings. How many times do I let them count? For a square root, I only let them count half of the time. And I pull those out in groups of 2, right? Because the denominator of the fractional exponent is 2. So as you see, as we go on here, you're going to see the pattern, and you'll have an aha moment, right? So let's go on then. You now know that 3 raised to the 3 power means what? It means 3 times 3 times 3. And that means that's 27. You see what I've done here? I'm raising something to the 3rd power. What it means is basically, if you think about what you're really doing here, when you cube something, I'm looking at a factor tree of this 3 right here. It's 1 times 3. There's no more factors I have. These are both prime numbers. So what's really going on here is when I cube 3, I'm taking all of the factors that make up 3, and I'm multiplying them times itself 3 times. So 1 times 1 times 1, but that does nothing. Then the 3 is 3 times 3 times 3, and so I get a bigger number, 27, right? But then later on, I'm saying, okay, then I'm saying, well, what is the cube root of 27, right? I'm saying that that's equal to 3, but the cube root of 27 is also written, I'm telling you now, as 27 to the 1/3 power, because cube roots are to the 1/3 power. But again, when you start learning, you're like, what does 1/3 power mean? What does that even mean? Like, how do you multiply that? I mean, that doesn't make sense. But this is what I'm telling you is the punchline. What you do is you go and you make a factor tree. These are the factors of 3. And then whatever the exponent is at the top, you're multiplying them basically that many times. You're letting them count 3 times. So the 3 is multiplied 3 times, the 1 is multiplied 3 times, boom, you get a big number. Now let's draw a factor tree for this one. You're going to have 3 times 9 is 27, and you'll have 3 times 3 is 27. So here's the factors that you have in the bottom of your factor tree. But now you're not raising it to the power of 3, you're raising it to the power of 1/3. So you're not multiplying them by itself 3 times, you're multiplying them 1/3. You're letting them count, for lack of a better word, 1/3 of the time. That's why we go down here and we start doing groupings of 3 and they only count once. Because when you raise it to the 1/3 power, what it means is you go look at the factors of that thing and you say, okay, they don't count. When you raise it, it's hard to say here. When you raise something to a regular power, you let them count the number of times of that power, 3 times multiplied. This one, you look at the factors, you're letting them count the number of times, for lack of a better word, as the power. But the power is a fraction, so they don't count more than, they get cut in the third. So they don't count, they only count for 1/3, and that's why we do groupings of 3, and so we said the answer is 3. That is the essence of everything I'm trying to get through in this lesson. And if it looks like I'm excited, I kind of am excited, to be honest with you, because when I first learned fractional exponents, I didn't understand it. It was just kind of like the teacher said, well, there are fractional exponents, and it's a square root, or it's a cube root, or it's a 4th root. Learn it. But the reason is because it follows exactly the same rules as regular exponentiation, or regular exponents. When you have a regular exponent, you take the factors of whatever it is, and you let them count this many times, and you multiply them. When you take a 1/3, you do the same thing. You find the factors. You let them count, quote unquote, this many times, but it's 1/3, so you let them count 1/3 of the time, then you get a 3. That is the essence of why fractional exponents are roots, why square roots and so on are the same thing. Because when we get down in here, when we have 4 to the 1/2 power, right? Well, let's do it like this. We have 4 to the 1/2 power like this. We do a factor tree. What is 4? 2 times 2. These are both prime numbers. I can't go anymore. So I let these factors count how many times. I let them count as many times as the exponent tells me, but it's only half the time. So I only count half of them, which means I get an answer of 2. And the same pattern follows for all of the roots. The 3rd roots are the 1/3 because they only let the factors count 1/3 of the time. The 4th roots are x to the 1/4 power because they only let the factors of whatever it is count 1/4 of the time, groupings of 4. Same pattern with 5th and so on and so forth. All right? Now, you understand why I wanted to bring this up now, because in the next lesson, I'm going to teach you properties of radicals. I'm going to teach you how to multiply radicals. I'm going to teach you how to divide radicals. I'm going to teach you what happens when you have a radical, like a 3rd root, a cube root, let's call it, and raise it to the 5th power, right? And you're gonna be confused if I didn't explain this to you, because those properties are just gonna come out of the blue from nowhere. But now that you know that radicals really are exponents, when you look at the next lesson and you see that those properties follow the same pattern as exponents, it will be an aha. It will be, well, they're not making up rules out of nowhere, they're just exponents. So they follow the rules of exponents, and that's why I wanted to put this first. Now that we have this kind of fundamental understanding under our belt, I want to show you one reason why they're useful. We're going to get into a lot of this stuff later, much later, but I want to give you a flavor for why it's so useful. Remember we learned a minute ago that if we have 2 squared and I take the square root of that, we said that the square and the square roots cancel, right? Because you all know that I can write this as 2 times 2, I circle a pair, and so the answer is 2. So the square and the square root operator cancel each other, so really the answer is going to be 2. We know that. But let's see what happens if we treat it the way we think we should treat it. What we're saying is the inside is 2 squared. I know it's 4, but let's write it as 2 squared. And now this radical, the square root operator, really is just raising the thing to 1/2 power. It's 110% mathematically equivalent to everything we've been doing to write this radical as just the fractional exponent. Now what happens here? What happens when we have an exponent raised to an exponent? Remember, if you have x squared raised to a 3rd power, like an exponent raised to an exponent, you just multiply the exponents. That is a rule of exponents. It has nothing to do with radicals. It's just an exponent rule. So this is a power raised to a power. It's just the powers of fractions. So what do? You multiply them. 2 can be written as 2 over 1 multiplied by 1/2. What do you get here? You get 2 times 1 is 2, 2 times 1 is 2, you get 2 to the 1st power, you get 2. So you see, even if you didn't know that square roots cancel squares, you know because we've done it that it's equal to 2. But even if you didn't know that, you would write it like this. 2 squared to the 1/2 power. You just multiply the exponents and you get an exponent of 1, which means you get back what you had on the inside. This right here, this multiplying of the exponents here, that really is the reason why squares and square roots really cancel. Because the exponent, which is a fraction for the radical, can multiply by the exponent on the inside, giving you an exponent of 1 left over. That's why they annihilate. That's a better way of thinking of it. That the exponents actually just combine to give you an exponent of 1. Right? And we can do something similar. Of course, we can do that with any radical we want. But for instance, if we have 3 to the power of 3 and we do a cube root of this, we know that the cube root is going to cancel with the cube. We know that. But let's do it a different way. Let's say we have 3 cubed and we're going to raise this. This cube root is now a 1/3 power. So what happens? We have a power raised to a power. So we treat it just like any exponent. It will be 3 times the 1/3. And 3 times the 1/3, you know, is just going to give you 3 to the power of 1, which is 3. This is why they annihilate each other. Yes, you can think factor trees. Yes, you know they annihilate. But the exponent raising to an exponent leads to the annihilation, so to speak, giving you back what is on the inside. And that is really, really powerful because when you start thinking about radicals as exponents, then suddenly you have a lot fewer rules to remember. Because I'm going to teach you the rules of radicals in the next lesson, but then I'm going to teach you that they're all just exponent rules, so you don't have to remember anything new. And if you don't have to remember anything new, then you have less stuff to remember, which is great, right? The next thing I want to tell you is, we're going to close the lesson here, is I'm going to tell you, just as motivation, we're going to do a lot more with fractional exponents later, but here's a motivation. What if you have x squared, and then you take the cube root of that? That looks gnarly, right? How do we do that? We did it before with factor trees, right? In fact, we can write it as x times x, but we're looking for groupings of 3, so we have nothing to circle. We have no way to really simplify that anymore. But let's now consider it as a fractional exponent. The x squared is what we're applying this radical to, which will be now 1/3. So we have an exponent raised to an exponent. So what we have is this exponent is 2 over 1. This exponent is 1/3. And so you multiply the tops, you get 2 on the top, you get 3 on the bottom. And here you have an exponent to the 2/3 power, which should give you shivers, like 2/3 power. What does that mean? Well, what that means is we take whatever's on the top of the fraction and raise to that power, x squared, and then we take the cube root of the answer, which is what we did. So when you see an x or anything raised to a fractional power like 2/3, you know right away that you're taking the cube root of it and you also are squaring it. That's what a fractional exponent is. The numerator of the exponent is if you're raising the thing to a power, and the denominator of the thing is the root that you're doing, when you're letting the factors count less and less, and so you're just doing the groupings. It's the nth root. So over here, when I introduced this thing, I said, This is 1/3. This is 1/2. Really, this means x raised to the power of 1, but then taking the cube root of it. X raised to the power of 1, taking the cube root. X raised to the power of 1, taking the 4th root. X to the power of 1, taking the 4th root. Now I want to do one more thing underneath here. Over here, now here's the crazy thing. I've done x squared cube root, and I've simplified it, and I've taught you that fractional exponents can be even more complicated, but they're actually easy to understand. The bottom means that you're taking a cube root. The top means you're squaring the thing first. But here, let's do this. Let's do this, which is different. X, we're going to take the cube root of x, and then I'm going to wrap the whole thing in parentheses, and I'm going to square it. So here I've done exactly the same operations, but in reverse order. Here, I've squared x, and then I take the cube root. Here, I take the cube root, and then I square the result. Same operations, different order. But now we know enough to write the x cube root as x to the 1/3, but then that whole thing is squared. We just wrote this as 1/3 power. But it's still an exponent raised to an exponent, so you have the 1/3 power here multiplied by the 2 over 1. So what you're going to get is x, 2 times 1 is 2, and 3 times 1 is 3. You get exactly the same answer, x to the 2/3, x to the 2/3. So you see what you've learned. It doesn't matter if you take the cube root and then you square it, or if you square it, then you take the cube root, you still get exactly the same thing. And this should not be a surprise to you, because now you know that these radicals are basically they are exponents, right? And if you remember, if you have 2 raised to the power of 3 and then you raise it to the 4th power, what do? You multiply the exponent. So you get 2 to the 3 times 4, you get 2 to the 12th power. This is the answer. But if you do it in reverse order, where you have 2 raised to the 4th power, and then you raise that whole thing to the 3 power. See, I'm doing exactly the same exponents, but in a different order. What you have, again, is you multiply 4 times 3, and so you get 2 to the 12th power. You get the same answer. When you have an exponent raised to an exponent, it doesn't matter which one's inside, which one's outside. You're going to get the same answer. So because of that, because radicals really are fractional exponents, it follows the same rules. So when you see an x to the 2/3, it doesn't really matter if you think about it as x raised to the power of 2 and then take the cube root, as we have written it here, or you can think of it as x cube rooted and then raised to the 2nd power, as we have written it here. It's the same thing. Because they're exponents, the order when you're raising one to the other doesn't matter. Now in the next lesson, I'm going to teach you some crazy rules of radicals. I'm going to teach you that when you have something squared or some kind of power with a cube root, I'm going to teach you what to do. But now that you know that these are all basically fractional exponents, the rules that I'm going to show you, they're going to look just like exponent rules. But the books won't tell you this early that these really are just exponents. So what you end up with is a whole list of rules that look really weird. Like, where do they come from? They come from the fact that all radicals really are exponents, but are fractional exponents. And I tried to motivate that by telling you, the first thing students say is, well, what is a 1/2 power? What is a 1/3 power? This one board is trying to get across exactly what I mean. When you take something, anything, and raise it to the 3rd power, you write down all the factors, right? And you let each one of these factors count this many times, and you multiply them all together. 1 times 1 times 1, 3 times 3 times 3. Okay? So then you get an answer. But when you have a fractional exponent like this, what you're doing is you're writing down all the factors, which is what we've done, but you let each one of them count only this many times. So this grouping of 3 only counts 1/3 of the time. So you basically do groupings of 3. That's why it works, and that's why it's a fractional exponent. So that is what physically a fractional exponent is. Instead of making the number get bigger, you're looking at the factors, and you're basically making it get smaller because you're looking for groupings, because you're only letting them count a fraction of the time. And that's the best thing I can do. And it was exciting when I first realized that, to be honest with you. Not because I am a math nerd, I guess, but not because I really care so much about math theory. It's just that I get very excited when I see that one rule that looks very different than this rule really is the same rule, right? There's no difference between the rules. That radicals are exponents. They're going to end up following the rules of exponents. And that's what we're going to learn in the next lesson. So make sure you understand this. Follow me on to the next lesson, where we will talk about properties of radicals, and you'll understand very rapidly where they're coming from, because they're all exponent rules.